So in the next one, we will try to plot the C of t value. For that, I'll draw the x and y axis. This is y axis, which is C of t. X axis. X axis is time. So we have C of t is equal to 1 minus e to the power minus t by tau. So this one, our response is r of t is actually 1. That is the unit step response. So u of t. And for t greater than or equal to 0, we are taking. So that value u of t for t greater than or equal to 0 is 1. So r of t is the desired response. It is the desired response. And C of t is the actual response. So we want, whenever we give unit step input to any system, we want this unit step change or unit step that is a waveform. Clear? So, but the actual one is different from the desired one. So first, let me draw the desired value. The desired one is nothing but the desired value. So this is equal to 1. Okay, and 1 minus e to the power minus t by tau. So e to the power minus t by tau. So we need to plot this curve. So e to the power minus t by tau is plotted something like this. Color. This is how e to the power minus t by tau is plotted. So this is the graph for e to the power minus t by tau. So approximately at very large value of t, for very large value of t, this e to the power minus t by capital T will be approximately equal to 0. Now we need to plot 1 minus e to the power minus t by t. So this will be somewhat in this shape. And after that it will attain the final. It will simply be, just redraw this again, very clear. Henceforth it will be steady. So this is 1 minus e to the power minus t by capital. Okay, so you can see that for very large value of t, this approximately becomes 0. So your final response will be equal to somewhat 1. So this is your steady state value. This is your steady state value. So after certain the transients are removed, after the transients have been eliminated, so this is the response that you get. That is the steady state response. So now we will define the time constant. So the time constant is the time taken for the signal to attain 63.2% of the steady state value. Now here the steady state value is 1. So the time taken to reach 63.2% of 1 is nothing but 0.632. We get this somewhere around here. 0.632. So at this point, whatever response time we get from the x-axis, so this is the time constant. Similarly, for t is equal to 2 times of time constant, then the c of t value will be equal to 1 minus e to the power minus 2t by t. So when we simplify this, we get this around 0.864. And similarly, if I take for t is equal to 4 times of t, so then c of t at t equal to 4t, this is equal to 1 minus e to the power minus 4t by. So this we get around 0.98. So somewhere here we will have 2t, and here we will have 3t, and somewhere here we will get for different range of time constant. I haven't derived the 3t value. So this will be somewhere around 86.4, that is 0.864. Fine. So now from this we can actually derive something called as steady state value. So the steady, oh sorry, not the steady state value, we need to define the settling time. So the settling time and the rise time are very important. Clear? So first we will look into the settling time. So settling time is the time required, is the time required to reach within 2% of the desired output. So this is settling time, 2% of the desired output. So that is settling time. Normally, whenever the output reaches 2% of the desired output, we say that we have attained steady state. Okay. Whenever the response reaches 2% of desired output, we say that, or it is said that, it is said that the steady state has reached. So how do we define, or how do we say when we actually get a steady state? So it is when your response is within the 2% tolerance of the desired output. So what we do here is that we draw this 2% envelope both above the desired response, below and above the desired response. So this is 2% plus 2%, and this is minus 2%. So if your response has reached within this envelope, within this pink envelope, we say that it has reached the steady state. So that is how we actually define the steady state. So settling time is the time taken for a system to reach that point, to come within that envelope. So this point. Okay, so this somewhere here we have this 2% one. So that time is nothing but a settling time. Now here in this normally your settling time is almost equal to 4 times the time constant, approximately equal to 4 times the time constant. Now how do we say that? Now graphically we have observed it is, we've seen that C of t at t equal to 4t is equal to 0.98. So it means that the response has reached within 2% envelope. So we can say that 4t is the settling time of the system, but we need to derive it. The derivation is nothing but the inverse of this. whatever we have taken this, the inverse of this simple if this equation will give us the settling time. So we will define the settling time, rise time in our next video. Thank you.